F324 June 2012, question 2. Question 2 gives you a nice little introduction telling you that part A is going to be about polyesters, part B about polyamides, and part C about proteins. So let's start then with part A. You've got a polyester A shown, and it's a degradable polymer. And one reason that it's degradable is because it can be hydrolyzed. So just as an additional question, whereabouts, if I was going to hydrolyze this polyester, where would it hydrolyze? Here we've got the ester link, haven't we, which marks the join between the two molecules. So it would be at that point there and at this point here that the ester bond would break and the molecule or the polyester would get hydrolyzed into its monomers. Another way that you could have polymer degradation is, well, there's one more we know, which is important with the C double bond O there. It can be degraded by sunlight. It's because that what we'd say is it would be photodegradable because it's got that C double bond O, which absorbs your UV radiation. It then becomes a sort of like a waxy compound which can then be decomposed to carbon dioxide and water by bacteria. But the key thing there is that the C double bond O in a photodegradable polymer absorbs UV radiation and breaks down from there. Part 2 then wants polyester A to be hydrolyzed to form compound B, and you've got to draw the skeletal formula for compound B. I wanted this to change colour, it's looking like it's not going to, but what we want to do here then, this end of the molecule, we've already said that we're going to split the molecule there. This end used to be, because it's not next to C double bond O, this end used to be the alcohol, so I'm going to put an H on there, and at this end I'm going to join. I've got this C here, haven't I, joined to the double bond O. This part used to be the carboxylic acid end and has an OH on it once you split that bond. So drawing this out in skeletal formula, we have the HO, which is joined to a carbon there, which has a group off, and then we're 1, 2, so we're just repeating the molecule essentially, but then putting on the two OHs. So there you have your answer for that one. On now to part B then, and polyamides. We've got nylon 4,6. Notice the numbers, of course, are relating to the number of carbons in each of the monomer. So nylon 4,6 here has butane 1,4-diamine and hexadioic acid. And what we're looking for here is simply to find out what the reagents and conditions are required for the synthesis of 1,4-butane 1,4-diamine from 1,4-dichlorobutane. So how do I go from a haloalkane to an amine? I've got to recall that I'm going to have, am I working here? Excess NH3. Remember that excess reduces the possibility of multiple substitution. However, of course, in this case, we do want a multiple substitution. We want both of those CLs to be replaced. So the excess here is not necessarily necessary, but we'll put it in anyway. But that is not good enough to get 1 mark. There's another condition. Well, if you like, we've got the reagent. We need the condition for this reaction. The condition we're looking for is something which is going to ensure good mixing, and it is our ethanol. So though it's quite key when you learn that reaction of the synthesis of an amine, phatic amine, so that's a straight chain amine. You need that excess NH3 and also the ethanol. Now, amines form salts with dilute acids. So first of all, explain how an amine can act as a base. Here you've got to be really specific, and I think I'm gonna, oh no, I'll stick with my pen. Here we go, it's gonna be a bit scruffy. Gonna be really precise. So there's a nitrogen in there. It's the nitrogen that has the lone pair, and you've got to be specific about that. So let's see how I'm going to phrase it. It has a lone pair on the N, which can, what can that lone pair do? Well, here we go. This is just what I thought might happen. It can accept a proton, and I think you might just have to take that without me writing it down. So it has a lone pair on the nitrogen which can accept a proton. It's all gone pear-shaped here for mine. For this final bit then, to avoid disaster, we've got the nitrogen lone pair accepts a proton. Gave up on the pen there, and I had to write this one in first. So we've got here that we've got our two amino groups, if you like, our diamino butane, and it reacts with an excess of dilute hydrochloric acid now, so in this second bullet point, and it's looking for the formula of the salt. So we've got hydrochloric acid, which is HCl, and it's an acid, so our base, as we've said, accepts a proton, so we've got our NH3+. Importantly here, one mistake that a lot of people made on this exam was that they didn't put both amine groups as their salts, so you're adding an H to both sides, and it's important as well that it's asked for the salt, not just the ion, so it's important that you put the Cl minuses on either side. What is not important is whether you put the plus and minus there. Since they've asked for a salt, you don't need to put the plus and minuses there if you want to. Here I'm just indicating that, remember, it's the nitrogen that has the plus and not the hydrogens. That is important if you're going to put your pluses and minuses on. Okay, to finish off our part on amines, we've got the two displayed structural formulas here. It's asked us to draw a repeat unit of nylon 4,6, which is using these two monomers, and it says clearly display the bonding that links the two monomers. So I'd suggest that, since it's asking us to display, and I've lost my cursor again, which is really frustrating, since it's asking us to display, that I would use displayed formula. So let's have a crack at drawing this. We want to lose this part, and we want to lose one of those H's. So we want to lose an OH there, and one of those H's there. So starting off, N with one H going out to nothing, then CH2 with the 4 around it, N, H. So my first monomer has lost an H from each side, and it's giving its wings. That is going to bond to the C double bond O, which is N lost its OH, and then I carry on my CH2, 4 of those, then back to my C double bond O. It's the monomer here which has lost an OH, and it carries on to form the bond which would come and form the next one with the nitrogen. Square brackets around, and there you have your two marks. What it's asked you to do is clearly display this bond, so I have here clearly displayed it. That's my peptide link, or my amide. So clearly displayed, and it's 1 mark for that and 1 mark for making sure that you've got the two complete monomers and you've not done anything with the ends of these. So for your monomer, you just take off the pieces that you don't need and draw them as is. Moving on then to amino acids, we've got this protein which we're going to have to hydrolyze and then turn into zwitterions. So we look for that amide link there, and we're going to split that between there. Now we're going to form a zwitterion. So first of all, these two amino acids will return to their standard formula. So this will return to OH, and this will get its H back. But then, since they're in their zwitterion condition, I'm pushing my luck here, trying to change colour, this H will move over to the N, and that is how you will form your zwitterion. You will have to put then the charge on here and on there, which is plus and which is minus. We'll see when I draw the diagram. So both zwitterions, and sorry, notice the difference here in the R group. So this has a R group with an alcohol, this an R group with an amine, and that is going to be important, that group, as we go down into the next part of the question. So to draw these out, I'm praying my pen is going to keep working. I've got CH down to my R group, which is an HOH and a CH3, and across to my C double bond O, and I've got an O with a minus on it because that H is moved over, and I've got an N plus with 3 H's on there. To the other side, it's again exactly the same, but this time I've got my different R group on. So there we've got the same condition with my, I've got an H up there. I don't know why it's doing black ink as well. And I'm down to a CH2 NH2. What is tempting with the zwitterions is to try and transform this group as well, which would be what would occur if I, for example, I was adding excess hydrochloric acid, for example. This would also become protonated, but when it's a zwitterion, you only ever deal with this transfer of the H from the carboxylic acid group to the amine group. So you do not, when it's a zwitterion, touch the R group if it has either an amine in it or it could be a carboxylic acid in there too. So you zwitterion, you concentrate on that transfer of the proton between the carboxylic acid and the main amine group, and you don't worry about what's going on the R in the R group. Coming down then, it tells you that they've got different electrolyte isoelectric points, and I'm going to make sure I use my text for this, otherwise it's going to get really messy. So these two isoelectric points, key thing here is only one mark. Why do they have different pH values? And you've got to, at this point, look at the R groups. Now this has got an amine group in it, and you do want that amine group not to be protonated at the isoelectric point so that the zwitterion forms. Because of that, because you don't want this group, this amine group here to react, it has to have a higher pH to form its zwitterion, so that this group doesn't become protonated, doesn't gain an H+. So this amino acid will have the higher pH isoelectric point in order to avoid protonation of that amine group. We don't have to write quite that much though in the answer. All they're looking for you to say is that the zwitterion with the higher pH has an NH2 group, and that's all they really want. But the zwitterion with the pH, with the higher pH, the pH of 9.6, has an NH2 group. I'm just saying it has an NH2 group because the other group, when it's a zwitterion, is an NH3 plus. So I'm just looking at that one group. I'm not counting this as being an NH2 because it's NH3 plus already. It's taken as read that at the isoelectric point that would be the case. So this has an NH2 group which causes that pH to be higher. It's tempting in this type of question just to say, well, oh, it's because the R groups are different, which is true, they are. But notice how, just like they want the nitrogen has a lone pair which will be donated, rather, so being really specific about things, here it's really, you've got to say, yes, the R groups are different, but they want more. They want you to say that the group, the NH2, will have the higher pH of its isoelectric point. So they do want you to be precise each time. It's not good enough just to give a sort of vague answer.